Hello everyone, in this lab we are going to learn about stress stiffening and buckling in ANSYS. These are the contents that we are going to learn and we will solve the problems using the ANSYS workbench. So first of all, I'll show you the details of the stress stiffening and buckling and then load multipliers, and finally there is one assignment. So what is stress stiffening? So stress stiffening is actually the bending stiffness which tells us about resistance to bending. So let's look at an example. Here we have a simply supported beam, and when we apply some lateral load at the center of the beam will deflect. However, if we apply an axial force on the beam on this right side, if this axial force is tensile in nature, this deflection will decrease. And if this is compressive in nature, the deflection will increase. So this effect of decreasing the deformation when we apply the tensile force is referred to as a stress stiffening effect. So this stress stiffening actually requires a nonlinear analysis if the deflection effects are very large. So when we talk about linear analysis, we look into this f equal to kx, and the ANSYS will solve this problem in a single step and will compute the deflections and stresses and strains. However, when we talk about nonlinear problems, it divides the applied force into small steps, like as we have previously seen, and then apply the loading, update the matrix, K matrix based on change in shape, and finally calculate the displacements again. And this is the iterative process. So this process is repeated for n number of n number of steps that we use for applying the loads. So let's look at the buckling and load multiplier. Here we have a simple column, and you can see that uh, there is this force P, which is pi square EI by L square, and it tells us that if the column is fixed on one side, so this is the minimum force that will be required so that this column will be unstable and the structure will fail under the buckling load. So what we actually want is we need to apply this load in the longitudinal direction, and this load must be less than the critical load for a particular boundary conditions. And if this load is greater than the critical load, that means that the column will buckle. So load multiplier is the ratio of the critical stress to actual stress, and we can look uh, to load multiplier as a safety factor, uh, which we define as the strength of the material divided by the actual stress that is occurring in the material. So this load multiplier is kind of a similar thing. Here it tells us whether the actual load is greater than critical load or not. So if load multiplier is greater than 1, the structure is safe, and if it's less than 1, then it will buckle. So let's look at a simple problem. Here we have a cantilever beam, and there is a force of 50 Newton that is acting at the end of the beam. The beam is 100 millimeter and the cross sections are 10 by 10 millimeter. And what I want to find is uh, the deflection of the beam when I change this horizontal force Fx from minus 500 to plus 500. Let's shift to answers and see what happens. So the first step is to model the beam in ANSYS Design Modular, and I'm going to use a line model of the beam and see what are the effects of the horizontal force that is acting on the beam. So first of all, I'll just open the Design Modular and draw the beam. So geometry is simple, and I'm going to sketch a simple line. First of all, I'll change the units to millimeter and then draw the line. So the line has a dimension of 100 millimeter. Let's change and convert this line sketch to line model actually. So here we have this one body, which is a line body, and now we need to define the cross section. For cross section, I'll just go to the standard rectangular cross section that we have in ANSYS, and its standard dimensions are already set to 10 by 10 millimeter. So I'll assign this cross section to the line body that we just created, and here we have a beam with 10 by 10 millimeter cross section. Let's shift to the analysis part. Okay, in the analysis part, I'll generate the mesh, which is a standard mesh, and it will be coarse here, and then apply the boundary condition on the line element. So the boundary conditions include um, so the beam, we can consider this beam as a cantilevered beam here. So I'll just change and add a fixed support at one of the vertex. And then there is a force that is acting on the second vertex of the beam, and its vertical component is always minus 500 Newton, and horizontal component is changing from minus 50 or and horizontal component is changing from minus 500 to plus 500. So let's set this to minus 500 and make this as a parameter so that we can evaluate the results multiple times in the parameter set. And next is to insert the directional deformation in y-axis. So this is the deformation that we want to find. So I want to check the maximum deformation of the beam. So I'll select this as the parameter. I'm going to close this. You will see that we have this parameter set here, and we can change the value of X force component and update all design points all at once. So let's change this to 250, 0. So this is minus 250, this is 0, this is 250, and this is 500. So let's evaluate these 5 design points and see how the deflection is changing as we are increasing the as we are changing from compressive force to the tensile force. After the solution, you can see that the results are not as we were expecting. So all of the results, they are 0. So there is one particular parameter that you need to take care of when parameterizing the details is whether the output that we are looking in parameterization tab is sign sensitive or not. So in this case, the deflection that we are finding will be in negative y direction, and it will be increasing in negative y direction. So since this deformation is directional and it has sign, so we need to parameterize the minimum deflection, which if we look in absolute sense, neglecting the sign, will be the maximum value. So I'll just parameterize this and go to the parameter set and reevaluate all of these details. After the second analysis, the result that we are getting have the same deformation value throughout. So what could be the possible cause of this? Let's move to the ANSYS analysis setting, and here I can see that the maximum vertical force that I applied here is minus 500 Newton, so it must be minus 50 Newton. so that we can clearly see the effect of the stress stiffening that I want to show. So I'll just change this again to minus 50, close this one, and re-update the results. The third iteration is also unsuccessful in reflecting the details of the stress stiffening, and the reason behind this is we are solving the problem as a linear problem, and we didn't change analysis setting to capture the non-linear effects that can result because of a large force in longitudinal direction of the beam. So since this is a cantilevered beam and we are applying a force of minus 500 or variable value in x direction, and then this force in y direction is, so when we solve this problem in ANSYS as a linear problem, so it does not takes into account the changes that are occurring because of this linear force. And to incorporate the effects of the stress stiffening, we must need to own this large deflection and then use the time stepping. It could be on or off. So I'm using the manual time stepping and inserting the number of steps as 10. And now if I close this and go back to the parameter set and update the points, you will see that the stress stiffening effects will be captured in this case. After the solution, you can see how the horizontal force decreases the deflection as we increase the force from compressive to tensile. So let's plot this force on Excel. After plotting, we can see that how the deflection changes as we increase the force. So when there is this positive force, the deflection decreases, and when there is this negative compressive force, the deflection increases. And if we extend this graph beyond this point, there will be a point. So this graph is not actually linear. This is kind of a asymptote where when we extend this, there will be a point and there will be a force at which we will get the almost infinite deflection. So that force is the one that we call as the buckling force, or we can call that as the critical load. Let's move on to buckling analysis and see what are the results. So if we want to analyze the buckling, you will see another module here on the left side, that is Euler eigenvalue buckling. And in eigenvalue buckling, you can click and drag and drop this eigenvalue buckling on the solution of the previous result. So when we do this and open the model, so all of the results from the previous texture analysis will be sent to the eigenvalue buckling problem here. So in this setup, I can go to the analysis setting and set the number of modes that I want to find. Let's say I want to find first 4 modes, and let's solve this problem. So the force and the supports, they will be taken from the structure analysis, since we linked both of these analyses based on the solution. When the solution is complete, I can see here in this tabular data the load multipliers that are available, and I can select all of these load multipliers and create the mode shape so that we can have a look at the shape of the buckling that can occur here. So I can simply uh, evaluate the result after generating the mode shape. So the first mode shape is, if I run this in the graph. So the first mode shape is the motion in is the buckling in Z direction, and the second mode shape is buckling in Y direction. And for these mode shapes, you see that we have these deflections here, but they are not of any significance here. So stresses and deformation values in buckling analysis, they are not of any value. Only the load multiplier is the one that we want to use. And the second buckling mode is this one where the beam moves in Z direction, and it makes kind of two different waves. So the smaller load multiplier here is 80.334, and it shows that the force that we have applied here, if we increase this force like by almost 80 times, then the column will buckle. So since the load multiplier is greater than 1, this beam is safe in this analysis in this case. Let's move on to the next part, which is the buckling analysis of a tower crane. And we designed this tower crane in previous lab that was related to the line model, and I'm going to use the already developed model in this case and perform the buckling analysis to check if this crane is safe or not. I have the crane here in this structure analysis B, and I'm going to insert the buckling tool here, which is eigenvalue buckling, and open the model. And after opening the model under given load of 6 kilonewton, we will see if the load multiplier is less than or greater than 1. I can solve the beam here first, and we can see that the maximum stress occurs here, which is compressive, and its value is minus 2.8 megapascal on this particular member at the top of the crane. And let's see if there is any buckling. So whenever there is this compressive stress, it's a good practice to go through the buckling analysis to check if that compressive stress causes the structure to fail or not under buckling. So I want to see the first 4 or 5 modes for the buckling and run this analysis here. After running the analysis, I can see that this load multiplier is minus 0.86, and all of these values, they are less than 1. So I'll just copy I'll just create the mode shape here and see the shapes of different kinds of buckling that could be occurring here. And let's run this. So this whole structure could be moving in this direction, and for this direction we have a load of 0.86, load multiplier of 0.86. Let's look at node number 6, and it can buckle like this. So that's the main point. So here the structure and the crane is not stable under buckling. What we can do to make it safe? What I want to do is to look at the lowest load multiplier here. Let's say this is the lowest load multiplier, and I want to parameterize this load multiplier so that we have the cross section, so that we have such a cross section that this load multiplier goes greater than 1. And in the geometry, let's go to the geometry of the crane here and select the cross section of the rectangle or square as the other two parameters. So we will be optimizing the base and height of the cross section. So in a way, we get the load multiplier greater than 1. We can run the optimization problem here, or I can discretely choose the parameter set as well. So I'm going to discretely choose the parameter set. Let's change this to 5 millimeter and 5 millimeter, 6 millimeter and 6 millimeter. Let's move, make it 8 millimeter and 8 millimeter, and then 10 millimeter and 10 millimeter, and update all of these design points. After updating the design point, I can see right away. So this is kind of a crude analysis that I did. So the best way was to use the optimization tool at just 5 millimeter base width and height. We get the load multiplier, the minimum load multiplier greater than 1. So let's change this and set this design point to current design point, and update this. When we update this design point, it will reevaluate the results, and I want to see the other load multipliers as well as a good practice to check if they are also greater than 1 or not. Once the design point is updated, I'll go to the model and see what are the other load multipliers for this particular cross section. I'll verify the details. So you see that the minimum load multiplier is now 1.75, and the others are have higher value. You might be wondering what is the meaning of this minus sign with this load multiplier. So this minus sign, it just tells us that if we increase the applied force, if we change the direction of applied force here in upward direction, so the crane can also buckle with this absolute load multiplier. So this way you can perform the buckling analysis and make your cranes and structures safe under the compressive loading. So this is the assignment for you, and this is a general pipe with different forces that are acting on it, and you need to capture the effects of the stress stiffening and then optimize the results based on the load multiplier here, and these are the deliverables if you want to find. So this it must include the report as well, so you can write the details what you see. Optimization of the pipe radius, you can read this and solve the assignment for you. Thank you so much, and we will be back with the next lab soon.